Very much. Good afternoon. So I'm going to talk about securing data use in the cloud. Try not to be too cryptographic at this time of the night or the afternoon. We all know that moving to the cloud has many operational advantages, and everybody wants to go there. But we also know that security in the cloud is a double-edged sword. On the one hand, actually for most companies, it's more secure to go to the cloud. Especially if you're small or medium-sized, the chances that you'll be able to secure a network to the same level that you'll get in the cloud is very, very small. However, there is the issue of a loss of control. When you go to the cloud, you are no longer responsible. You have to rely on somebody else. It's not working. Okay. So this loss of control actually has a psychological effect, and I like to compare it between driving your car and taking a flight. Most people, I don't know why, it's not true for me, but most people are more afraid of flying than they are of driving. I think there's a much bigger chance to get killed on the highway to on the way to the airport. But people are more afraid of flying because they lose control. They're not in control of their own safety. That'll also actually be the biggest obstacle, I think, for self-driving cars. And it's the same thing when you go to the cloud. The fact that you are no longer in control and you have to rely on someone else is a concern that people have. There's also the regulatory issue of some data having to be in your control and you're not being allowed to export it elsewhere. The real threat, however, is being caught up in a mega breach. So if you have your data in your own network, then you have control over it, and if someone wants to come after you, then there's a good chance they'll get to you. If you go to the cloud, you may be breached for no reason whatsoever apart from just being an innocent bystander. And this has actually happened. It happened to Dropbox. So in 2012, attackers breached LinkedIn, stole the password file. Unfortunately, LinkedIn at that time did not salt their passwords or even hash with iterations. It was a simple hash on the passwords. So the attackers built a rainbow table and dumped the entire password file, or the almost entire password file on the internet. A Dropbox employee had actually reused his work password at Dropbox for his LinkedIn account. Obviously, very, very stupid thing to do. But attackers used that password to actually access the Dropbox user password database and dump 68 million credentials online. These passwords were actually hashed properly using Bcrypt, but with not too great an effort today, you can still break them without much difficulty. And therefore, this is exactly the fear of being caught up in a mega breach. So not only was Dropbox compromised because of LinkedIn, but anyone who used Dropbox was compromised because of that. And that is the main problem and concern that people have. So all Dropbox users are caught up in this breach, including those that are using it for work, and there are quite a few of those. So how can we protect our data in the cloud? Well, if it's data at rest, which is actually pretty much the Dropbox case, right? So we have files that we want to encrypt online, then it seems very simple just to encrypt. But even for this very, very simple case, it's actually not so simple because there's a question of where you're going to put the key and how you're going to protect it. So here are a few options. One is you keep the key and you only export encrypted files to Dropbox. This actually can work for Dropbox, but it makes the cloud a dumb disk. That's all the cloud is. It's something which can hold encrypted files and allow you to retrieve encrypted files. You can't even search on those files. It makes it a very, very dumb and not very useful thing anymore. The second is to store the key on the VM together with the data. This is obviously a joke and something stupid to do, although we heard just a few talks ago about that this actually is done sometimes, and you can find cases where encrypted data is stored right next to the key that encrypts it, and we know what that means. It's completely worthless. It's not working. Okay, and the third option is to have the keys being managed by the cloud. Once again, it's a loss of control, regulatory problems, can you trust? What about subpoenas? What about other issues? Is that you allowed from regulatory aspects? All of these are actual problems. So I want to go to the next step, which is not encrypting data and making the cloud dumb, but enabling us to encrypt data and hopefully try to keep some functionality. So we're all familiar with data in motion encryption and data at rest encryption. but we want to utilize the power of cloud computing, and therefore we don't want to use either of them. We don't want to use just data at rest encryption. So I want to talk about a new paradigm, which is encrypting data in use. So the data is encrypted by the client, possibly at a proxy, uploaded to the cloud, and the cloud then can carry out computations on that data while it remains encrypted without the cloud ever knowing the key. And therefore, even if the cloud is breached, they should not be whoever breaches the cloud or the cloud provider should not be able to learn any information. And then the client can retrieve the data after the computation and decrypt. That's what we would very much like to have. There are two actually very, very different settings that consider this type of functionality. The first, on the left, is that of is one where we don't even touch or change the cloud provider at all. So as far as we're concerned, or as the cloud provider is concerned, they operate in exactly the same way on the encrypted data and on the plain data. This is obviously very, very attractive. On the right-hand side, though, we can think about a modified cloud service where the cloud does actually know it's encrypted and therefore will behave in a different way to operate on that encrypted data. So an existing service is obviously very, very easy to use. It's very easy to deploy, and it uses just existing infrastructure. So this is what everybody really, really wants. This is the holy grail that everybody wants. I don't need to touch my cloud. I just encrypt locally, and everything works perfectly without making any changes. However, it has severe disadvantages in that it limits what can be done. And we'll focus quite a lot about the severe inherent limitations of this model. In the second model, where we modify the cloud, we have the advantage of more flexibility. Now I can encrypt and have special instructions that allow the cloud to operate on encrypted data. And this obviously has a disadvantage that now you need the cloud provider to cooperate. They have to change their code, they have to change their service, and deployment is a much, much more difficult task. So let's talk about the first setting initially. We're not changing the cloud service at all. And the first obvious thing to do is to just encrypt deterministically. Let's think about, all we're talking about for now is just searching for keyword search. We want to retrieve all the files that have a certain keyword or all the emails that have a certain keyword. If we decrypt each term deterministically, then we're just replacing each keyword with another keyword. It may not look like a keyword, but it's just a simple replacement and substitution, so search still works. Technically, you can apply what we call a pseudorandom permutation. I'm not going to go into the details of how you do this efficiently, but this can be done without any problem. So search is maintained and everything is fine. There are a couple of things that are important to note. First, partial word search functionality is completely broken. When we search in our email, if I want to use this for Office 365, when we search in our email, then we start typing the word and we expect to start retrieving hits on that search. Especially if the word is long, this is something which is very important to us. If you try to implement partial word search with deterministic encryption, then everything becomes completely useless because you're essentially encrypting each character separately, and that's a substitution cipher which is even more crap than this, as I'll show later on. The second thing which is important to note is that the output of a deterministic encryption scheme does not necessarily have an appropriate format anymore. So let's think about a database service that knows that a certain record has to be a credit card number and another one has to be an address, a phone number, date of birth, and so on and so forth. If we try to encrypt using AES or a standard block cipher, it may be deterministic, but the format will be broken. We can actually solve this problem. It's called format preserving encryption, and it can be done efficiently, and you can actually replace random credit card numbers with other random credit card numbers and still keep the format perfectly, even if there are checksums. But that's not my focus today. I want to talk about the security aspects and the functionality aspects. It's just worthwhile noting that this can actually be done. Okay, so let's assume for now that we use deterministic encryption, and it's perfect deterministic encryption. This means that absolutely nothing is revealed except when the same term is encrypted twice. And that's the only piece of information that I need to now carry out attacks on this scheme. So it's absolutely perfect. Just assume the only flaw is that when you see when the same word is encrypted twice, it's encrypted to the same thing. That is actually inherent when you're using deterministic encryption. So is this good enough? One answer that people often say, well, if it's the best possible, then it has to be good enough. Okay? And my answer to that is that, well, actually the best possible depends on the model. So if you come along and give me a constraint and say, okay, I need to encrypt to the cloud, and I cannot change the service on the cloud, then what's the best way to encrypt? Then my answer will be deterministic encryption. But if the next question is should we be using such a solution in the cloud? That's a completely different question. And we don't have to use a solution that doesn't require changing the cloud. It's easier. It's easier to deploy. It's faster. It's less costly. It doesn't mean it's the right thing to do. And we also don't even have to recommend going to the cloud for all types of data and without understanding the security aspects enough. And I want to stress that a lot of people say, no, it's okay. I understand that deterministic encryption is weak. I understand that I'm not getting all the guarantees of standard encryption, but it's better than nothing. Well, you know what? It's not always true that it's better than nothing. Sometimes more security is actually less security, because people have the understanding that, yes, we are now encrypting to the cloud. Therefore, it's okay to move sensitive data to the cloud that otherwise maybe we wouldn't have moved that data. Or maybe we can reduce other controls. Maybe it's not that important to have some other state-of-the-art protections because we're actually encrypting, so what's the problem? So more security can be less security, and it's not necessarily a good idea to say it's fine because we're just adding another layer of security if you don't really understand exactly what you're getting and not getting. So let's try and analyze this a little bit more in depth. The same word is encrypted to the same ciphertext word every time. So obviously we can gather statistics about the frequency of different terms as they appear in the original text. That's something that we can always do. Now, because natural language has a very specific distribution, if you encrypt all words using deterministic encryption, then you can actually learn a lot about the text just by doing a standard statistical analysis about the frequency of terms. It doesn't mean that you can't use this at all. One classic example where deterministic encryption works very well is when you're encrypting unique values, like a key attribute in a database that will appear only once. It may be someone's ID number, maybe a credit card number, but if that appears only once in the database, then it's definitely fine to use deterministic encryption. It's important to note, though, that it doesn't mean that credit card numbers are always fine to encrypt using this way. If you have, for example, a database of transactions, and for each transaction, you have the transaction name, its type, etc., and the credit card that was used to carry out that transaction, then if you use deterministic encryption, it's now possible to have a look and see exactly what one specific person bought, or actually any person. You can bunch the transactions together and see who bought what. And if you have some partial information about what I bought on a certain day, you can now, by looking at the encrypted database, learn everything else that I bought as well. And that's specifically the problem with these things. Okay, so here's a stupid example. Here's a database with 4 items, a health database with illness, and this is the way it looks when it's encrypted. So obviously, if you have auxiliary information about the fact that I have diabetes, which I don't, by the way, but if you had that auxiliary information, then you would know automatically that Mike Jones also has diabetes. Likewise, if I get access to that database and I have my record where I know what those values are, then I can now learn about other people as well. This is the standard problem of auxiliary information. And auxiliary information exists in the world to a very, very great degree. So let's look at a real-life example. If you all remember, a couple of years ago, Adobe was hacked, and their password file was dumped on the internet. For some very, very strange reason, Adobe didn't hash their passwords. Instead, they used DES, or something to that effect, deterministic encryption. It was even because it's DES, so if you had a long password, it would be split into 2 different parts. And here are some of the examples. To make things worse, you had password hints that are in the clear. Now, what this means, if you look at the first bunch of 3 passwords, you know that all of these people have exactly the same password. Okay, but the first person said exactly what, well, they all said, so they're all stupid. But the first person said that their password is 1 through 6, and now we know that the other ones are also 1 through 6. Okay, so if you look at the second bunch, one person just said numbers. If they just said numbers, you don't know what their password is just by looking at their password hint. But the next person said it's 1 through 8. So now we all know that the first one is also numbers. And of course, there's the guy who thought that saying rhymes with the ass word hides what the password is. Yeah, so that's the funniest one there. But this is a real-life example of what looking at deterministic encryption and looking at what it means to have auxiliary information. Let's look at something much, much more interesting now. So this is work from a paper that appeared last year at ACMCCS. They analyzed what would happen if you encrypted real health databases using deterministic encryption. And what they did is they said the following. There's this project called the Healthcare Cost and Utilization Project. It's a database that's generated every year based on hospital data from across the United States. And you have controlled access to this database only. They're fully aware that there is sensitive information here, so it's only controlled access. The researchers got that controlled access, and they said that we're going to encrypt the 2009 database using deterministic encryption, and we're going to use the 2004 database as auxiliary information. This makes perfect sense. The database is actually real patient data, saying each patient, what operation they had, how old they are, how long they were in hospital for, did they die or not, how severe their illness was, and so on and so forth. And now we're going to look at the 2004 database, which is completely different patients. But it gives us auxiliary information about the statistics of hospitalized patients in the United States. And all their attack was the stupidest attack possible. They didn't use any information about how the deterministic encryption worked. All they did was build a histogram of the different clear text values from the 2004 database. They built a histogram of the encrypted database from 2009, and they compared them. And they said, well, if the most common illness in 2004 was flu, then we'll assume that that's also the case in 2009. And this is the result. I'll try and help you read these graphs. The graph on the left, or actually both graphs here are the cumulative fraction of records recovered. They're only talking about exact recovery, so they're only counting a success if they know 100% for sure exactly what the value was. Obviously, if they were allowing themselves to have a guess between two or something, the result would be even better. And these lines, basically, when you go from left to right, that tells you what percentage of records were recovered, and from the bottom up tells you what percentage of hospitals you managed to recover that amount of records. So you can see this purple line going down, which relates to the major diagnostic category. So that's the worst. That's their worst item. But you can see that, for example, in about 40% of hospitals, they could recover about a third of those items with 100% accuracy. Okay, so that's a lot of recovery, and that was their worst item. You have things like disease severity, which they did much better at. At 60% of the hospitals, they could get everything. Sex, mortality risk, patient died during hospitalization, and race, they could get almost all information all of the time. On the right-hand side, things like age, length of stay, primary payer, and so on and so forth, they managed to recover most records with very, very high accuracy. Even ones which look not so good here, so for example, the age, it doesn't look great, but you can still see that for 100% of the hospitals, they could recover 20% of the ages with 100% accuracy. Okay, that's a very, very significant breach. So if you're going to release a health database which is encrypted with deterministic encryption, then you should be aware that between 20% and 100% of all the values can be recovered with 100% accuracy. And if you're willing to allow some small error, then you'll get much, much more as well. So that's what deterministic encryption looks like in real life. I want to talk about another type of attack, which is what would happen if you try to use this in Office 365 email encryption. Okay? Then, and now I want to assume an attacker who has access to the encrypted database, but obviously not to the key. right? Because that's exactly the model. The key is at a proxy at the organization, and all the emails are encrypted as they go out and decrypted as they come in, and the database in the cloud knows nothing about the key, but obviously we're worried about an attacker who gets to that database. Now here's a really trivial attack, okay? The attacker simply sends an email with the keywords of interest to an employee in the organization. That email gets sent to the employee, is then encrypted at the proxy and sent out to the cloud, encrypted under the same key. The attacker can simply now look at the keywords that were encrypted. He knows what the email is, so he knows exactly what those terms are, and can search and completely decrypt all of those keywords in the entire database of that organization's email. Okay, this is a completely trivial attack, and there are many. By the way, there are a number of companies, a number of startups out there who this is what they're pushing. I think someone gave a statistic that last year or last few years, a couple of hundred of millions of dollars has been invested in startups who are doing these types of solutions. And what you have to understand is for applications like email, for example, it's completely worthless. Completely worthless. So it's a very, very easy attack to carry out. Okay, problem with this clicker. Okay, let's move on now to the next topic, which is order-preserving encryption. Okay, so if things were bad beforehand, they're now just going to get a lot worse. So what's order-preserving encryption? It has the property that if you have two plain text values x and y, and x is less than y, then the encryption of x will actually also be less than the encryption of y. Okay, it sounds very strange. How is that possible for encryption? Encryption is supposed to somehow mix up the plain text, but it can actually be done, and in the following sense. The idea is that we take a relatively small domain of plain text, and we throw it randomly into a very, very large range. Now, the idea is that if the range is very, very big, then when you look at a single item, you actually won't know very much about the original plaintext value. So if 3 is mapped to 11, in this example, when I look at 11, maybe I'll have a reasonable guess that it's not 1 or 6, but I definitely won't be able to know if it's 2, 3, 4, or 5. And typically these schemes, the proposal is to throw the domain into really a massive range, and therefore you'll have very little information, or that's the intuition, you'll have very little information about the plaintext given the ciphertext. Okay, that's the way these schemes work. You can actually compute this efficiently, which is a little bit surprising, but this can be done even with rigorous proofs that you have something which is a random order-preserving function in this massive range, and therefore so-called preserved security. So here's another stupid example to start with. Like beforehand, I have diabetes, but alongside my illness, we also write down my blood sugar. But if we look now at the encrypted version of this database, then the attacker, just by looking at the static encrypted database without doing anything else, can immediately see who has the highest blood sugar. And if you know that Mike Jones has the highest blood sugar just by sorting the encrypted values, then you also know that he has diabetes. Okay, so obviously there is very simple information which is leaked by this. Once again, the idea is to try and have a look what happens in real databases, in real world situations when you try to apply solutions like this. So exactly the same scenarios beforehand. We're talking about the same health database using 2004 as auxiliary information, 2009 as the encrypted database, and now we do exactly the same thing. We sort what the 2004 database and compare this to 2009 database. Now here it's obvious that if you have values with high density, then you'll always be able to fully recover everything. For example, if it's a hospital and we look at a person's age, there's a very good chance that we'll have all the ages when we look at patients who are admitted to the hospital. And if we have all the ages, then you can look and see that the 83rd value in the sorted order will be someone who's 83 years old. Okay, so obviously when things are dense, then order-preserving encryption is completely useless. But the hope is that when data is sparse, we'll get some reasonable level of security, and that's what we're hoping for. Unfortunately, that's not the case. So here on the left-hand side, you see the density of the values. So for example, the length of stay is not very dense. But on the right-hand side, you see that in all the types of values, the recovery is almost 100% in 100% of the hospitals. Okay, so just by sorting and comparing to what happened 5 years ago, you can, and again, this is exact recovery. They didn't consider it a success if they missed by a little bit, and that proves the power of this attack. If they were willing to say, okay, I'm happy to know if the person is approximately 70 years old, then they would do even better. In a case with a small hospital, you have a lower density of values, so you would hope that things are going to be much, much better, and they're still very, very bad. You're recovering in most of the values 100%. In a couple of them, you're getting only about 90 or 75%. Okay, so this means, again, in reality, applying this even on non-dense values is complete garbage, and it's not worth even calling encryption. But I want to try and think about something else now, which is using this for location data. Why would I want to use this for location data? For two reasons. Firstly, location data is very sparse. If I look at just GPS coordinates, then this is very sparse data if I just take my GPS coordinates over time. And therefore, I could conjecture that order-preserving encryption could actually be useful in such a scenario. Another reason why I'd want to do this is because I'm not sure how many of you out there are aware of this, but location data is probably the most sensitive data you have. In fact, I think I would prefer someone to see my medical data than my location data. If I know your location data, I know where you live, obviously. I know where you work. I know who you meet with during the day. I know where you shop. I know who your friends are. I know when you have stops at night at some place for a couple of hours when you shouldn't. I know everything about you. I know what business meetings you have, and therefore also for purposes of industrial espionage, I know absolutely everything about you. Once I actually saw real location data, and it was very, very scary. So this is a database of someone in Germany, a privacy advocate who demanded from his phone carrier to provide him all of his location data, because phone carriers have all of this. And he actually released it online because he wanted to show people how powerful it is. That's what you see at the top. And what these researchers did is they did something very simple. They encrypted these coordinates using order-preserving encryption. And now this is sparse data, and it's encrypted using order-preserving encryption, so it should actually mess things up. And all they did now was plot the data points, because you have X, Y coordinates. They plotted them and saw what came out. And what you see is that even for this very sparse data, it's very, very clear what the original, it's very, very close to the original. Now note that if I know this person lives in Germany, and I look at this right-hand side graph, and I know something about the road system in Germany, I can pretty much put this on just one single place. So even encrypting location data is really, really worthless, and this shows it very, very, very clearly. Here's another example. They took, there's a database of 20,000 intersections in California. They took a random sample of 2,000 and wanted to see what it looked like. This is what it looks like when you plot it. It's almost exactly the same, and they could pinpoint with very high accuracy which of the 2,000 intersections were actually encrypted, chosen and encrypted, even though it's order-preserving encryption. Likewise here they did a different attack where you look at the higher order bits. If you think about it, since I'm randomly throwing out into a database, I can actually look at the higher order bits and guess if I'm a small number or a large number, and this turns out to also be very, very effective. So here they don't know what part of the world you are, but it's very easy when you see that image and that form, you know that that's California, and therefore everything is once again revealed. Okay, so deterministic and format-preserving encryption are not secure. There are very specific use cases where it's okay, like unique values for tokenization or something like that. Otherwise, it should not be used at all. It should not be considered a reasonable measure of security. Order-preserving encryption is even worse. And note that When I say auto-preserved encryption, I'm talking about something which is fully ideal, the best possible auto-preserved encryption in the world, because all of these attacks did nothing but sort. All they did was sort, and look at what came out. And they had such a high accuracy. So I would personally call these encodings rather than encryption. In fact, I would argue that they should not be used at all, except for the specific case of format-preserved encryption that I talked about. Okay, so let's move on to the second setting and say we have a proxy at the gateway as well. The proxy will encrypt the data as it goes out, but now my cloud provider will be modified to know that they're actually going to receive encrypted data and they can possibly do more. So what can we do? For example, can we at least have probabilistic encryption? We know that's an absolute must because all of the previous attacks were based on the fact that encryption is deterministic. So in theory, we can do everything. Okay, if you haven't heard, there's something called fully homomorphic encryption. You can compute anything over encrypted data, and nothing whatsoever is revealed to the cloud provider, and this is wonderful. Practically, though, it's way too inefficient for most problems. There are some problems where we can actually do something reasonable. Actually, the group in Microsoft Research in Redmond actually had some nice work about doing classification on some genomic data using this, but it's for very, very specific problems that you can formalize in a very specific way in very, very low depth circuits. So this is not suitable for the sort of things that we've been talking about until now. What we do have is something else called probabilistic searchable encryption. And this is a method, I won't go into detail of how it works, but this is a method you can actually encrypt each search term probabilistically. So the same term will look different each time it's encrypted. And now you have protection against, full protection against what we call snapshot attacks. If someone looks at the database, they learn absolutely nothing just by statically looking at the database. But in order to search, the client will provide something called a search token, which will enable the cloud to check each term whether or not it's the one the client wants to retrieve. That's the only information that can be retrieved. This can be constructed very efficiently, and unlike fully homomorphic encryption, it does reveal information. It reveals what we call the access pattern, but only the access pattern. So it reveals which term is, if I'm searching for the same term twice, I'll see that because the token is deterministic. And it will reveal which documents are retrieved in each search. Okay, so again, security against snapshot attacks, we have that. And the search patterns are revealed, so I know if I'm searching twice with the same token, and if two documents are returned together, then I know that they have the same search term. Because someone searched for something and those two documents were returned, that means they have the same keyword. Likewise for two transactions in a database. So now let's look at the security of this. This is much, much better than deterministic encryption. And you can't do any of the statistical attacks, the naive statistical attacks that we did beforehand. So here's a work that was published very recently about what happens when you can inject documents into the encrypted archive. So let's look at a warm-up case of an attacker. So we think about a case where an attacker can somehow get a file of his choice to be encrypted under this scheme and placed in the database. Then an attacker could encrypt half of the keywords they're interested in and encrypt that prepare a file with half of the keywords they're interested in and put that file into the archive. Then when any search is carried out, the attacker can have a look, was this document retrieved or not? If the document was retrieved, then they know that what was queried was one of these keywords that they were interested in. Okay, that's a very, very simple first case, but we can actually generalize this very nicely. Let's say we have a number of keywords K. You can think of K being 1,000,000. There aren't 1,000,000 keywords in practice, but let's just say 1,000,000. And now what I do is I'm going to generate log K documents. In the case of 1,000,000, I'm going to generate 20 documents. And in in the ith document, I'm going to insert all the keywords where their ith bit equals 1. Okay? And then I'm going to inject these 20 documents into the archive. If we think about the Office 365 case again, so I'm going to send 20 emails. That's all I need to do. I send 20 emails. Each email has this encoding of the documents. Now, when any query is made by the legitimate user, the attacker can look and see which documents are retrieved. Notice this, all this attack does is look at which documents are retrieved. So it's access pattern only, and I'm assuming that everything else is 100% perfect. But if I see that the first, second, and last documents of the 20 that I injected are retrieved, then I know exactly which keyword was searched because I have this encoding of all of the keywords. Okay, so this enables the attacker to see exactly what keyword was being searched for. Not only do they see exactly which keyword, they also know exactly which of the documents in the database have this keyword because they see all of the documents being retrieved. So again, if you can inject documents, then even probabilistic searchable encryption is far from satisfactory and very, very weak. Okay, so some attempted countermeasures are to say, let's limit the number of keywords in any document. So we won't allow you to encrypt something which has so many keywords. Actually, the paper has a different attack which bypasses this, so that doesn't work. A second thing you can say was, let's do semantic filtering and check that the document being injected actually makes sense. But you know that you can almost write scientific papers automatically today. So you can easily generate text based on a set of keywords that makes perfect sense. So this also won't work. Probably make a lot more sense than half the emails that I get. And in conclusion, if file injection is possible, then even probabilistic searchable encryption is simply not satisfactory. When may it be helpful? In a much more closed setting, like a database warehouse with authorized upload or something to that effect. For email, it's certainly not a reasonable option. Okay. Another thing that these researchers did is they also looked at what about a known plaintext attack. So I know a few emails, and I want to look at everything else, and this is, and I want to see how much I can retrieve from that. So they took the Enron email database, which is a massive database. I think it has over 1 million emails or something. And they took just 20 random emails and assumed that they know these emails in the plaintext. And they looked at the access patterns again and saw what could they learn about other emails. They took a random email, and you can see here that they could actually learn almost all of the important terms in the email. So this is also very, very problematic. So the downside of probabilistic searchable encryption is that if you have chosen document attacks, you can completely break the scheme very easily. And even if you have just known document attacks, then they're also very effective. Finally, one of the big problems is that you have this very vague concept called access patterns, and people don't really know what that means. It's very hard to pinpoint, and so people have this false sense of security. Looking at what actually happens on real databases shows you that actually the level of security is much lower than thought. The upside, however, is that you do get full security against snapshot attacks, and these are still the easiest attacks to carry out. And also the attacks do require sophistication and power. You need, for example, have to run code on the server, and you need to be resident there for a long time in order to gather this information, because you can't just look and see. You have to wait and see what is retrieved all the time. In my opinion, this encryption method has been proposed for two types of threat models. One is where I don't trust the cloud provider. In this case, I don't think that it provides good enough security. Because if I don't trust the cloud provider, that means that I don't trust the information the cloud provider is learning from the access patterns. And they do reveal a lot of information. However, if my threat model is different and I don't want a curious administrator to be able to learn information, or I'm worried about a possible breach to the cloud provider or to some other server, and then typically hopefully it won't be a very, very long breach going over a very long amount of time, then maybe I'm getting a better level of security, but it's something which still requires further research. Another technology that can possibly be used to help is something called secure multi-party computation. This is something that's been studied since the 80s and basically enables different parties with distributed data to compute functions on that data without revealing anything but the output. That's all they reveal, nothing about the input. It's a typo on the slide. Nothing about the input is revealed, only the output. It's actually become practical very recently, and we can compare DNA without revealing it. We can carry out cryptographic operations on keys that aren't found in any single place. We can verify biometrics without revealing the template. These are very nice things that we can do, and these are all practical with today's technology and multi-party computation. So one thing that we've proposed, and we've actually played around with this a little bit at Dyadic, is to try and get secure SQL for a very rich language amount of the SQL language by combining probabilistic, searchable encryption, and multi-party computation. So the idea is we take a database and we share it in random shares over 2 servers so that no administrator to any single server can see anything about the data. It's fully secure against a snapshot attack. And then the way this would work is that the first thing to do is to filter by unencrypted values if you have that. If, for example, if you don't consider the date of a transaction to be confidential, then you can just simply have that unencrypted and you can just filter that immediately. The next thing you do is you filter all the where equals clauses using probabilistic searchable encryption. This reveals access patterns like probabilistic searchable encryption, but no more. And my aim now here is to get a richer functionality, not just search for equals, but also to enable everything that SQL gives you, comparisons, joins, grouping, group by, and so on and so forth. Once I've finished the filtering by where equals, I now run a mixnet, which basically means that I completely re-randomize the shares of the databases that I have. And this is in order to try and break access patterns from one query to the next query. So you can get the access patterns only from the probabilistic searchable encryption, but from that point on, the parties actually hold fresh re-randomized shares of the database that they can't connect back to the original database. And then all the greater than type clauses or like and other things are run using secure multi-party computation. You can aggregate and compare as well using additively homomorphic secret shares, which are included, and join and group by. All of these functionality is actually fully supported by this scheme. And we actually experimented with this, and we showed that in using a cluster of 3 reasonably strong servers or mid-level servers, you can actually get performance which is within an order of magnitude of standard PostgreSQL. Okay, so this can actually be done. You can actually get good performance. You have to add hardware, but you can get good performance with while still maintaining quite a high level of functionality. And this shows that more can actually be done beyond just searching for equals. Again, you do have the issue of access patterns here, but they're limited only to the probabilistic searchable encryption. Okay, so that's the security that I mentioned beforehand, access patterns only, and the mixnet prevents anything more. In summary, encryption in the cloud is very, very difficult. In fact, even if you're just worried about data at rest, the issue of managing keys, where you put them, how you keep them safe is actually very, very difficult. For data in use, the situation is obviously much, much worse. You can't use standard strong encryption that we'd like. The potential of deterministic, or the promise of deterministic and format-preserving encryption, in my opinion, has not been achieved. It's not secure, and it should not be used except for very, very limited settings. Order-preserving encryption is extremely weak, and in my opinion, should not be used at all. Okay, it's not encryption. Even if you want to call it encoding, maybe call it, I don't know, similar to XORing everything with a fixed string or something like that. Probabilistic searchable encryption is actually much better. You get full protection against snapshot attacks, which is important. But they can be attacked using more sophisticated methods like the known document or document injection attacks that I mentioned beforehand. They're also much more effective when the threat is an outsider and not that I don't trust the server. Finally, as we mentioned, if you combine probabilistic searchable encryption and other techniques like multi-party computation, you can actually get even higher functionality. Thank you very much.